Welcome to Chemical Process Safety. This video is going to be about inerting. Now, there's two possible regimes of inerting. There are cyclical inerting processes and sweep-through inerting processes. This video, we're going to focus specifically on the cyclical, and in the next video, I'll talk through the sweep-through. So in the cyclical inerting process, we can do it one of two ways. We can either do a vacuum purge, and the cycle for the vacuum purge consists of 3 steps. Step 1 is pulling a vacuum, and this just means evacuating or sucking out the materials that are inside the vessel already. Note that this does not have to be a complete vacuum, just has to be partial. The next step is we relieve that vacuum with an inert gas, and then we just basically alternate those two. So we pull a vacuum, we relieve with an inert gas. The other one is pressure purging. We'll talk about that one in the second half of the video. And the pressure purge, the difference is we switch the order of the steps. So in a pressure purge, we're pumping in more gas to pressurize the vessel, and then we're venting by relieving it. So a typical problem that we'll see is calculating how many cycles we need to do. And this is going to depend on a number of different parameters. So I'll show you the equations in a moment, but before we do, let's go through the derivation because I think that can really help with understanding where the equations come from. So I like to derive them by considering the initial mole fraction of oxygen inside the vessel. Oh, and I should also mention that vacuum purging is good for reactors and small vessels. And that is because the vessel that you use will have to be able to withstand vacuum conditions. And the smaller the vessel is, usually the stronger it is towards vacuum. For large vessels, if you pull a vacuum, it could potentially crumple inward. Even though many vessels tend to be built to withstand high pressures inside, not many are built to withstand lower pressures inside. So anyway, the initial mole fraction of oxygen we'll call Y0. And for regular air, or we'll start off with Y0 being 21%. We'll call the initial pressure P high, and we do that because the other pressure is going to be P low, and for a vacuum purge, that is going to be lower pressure than the regular pressure. The corresponding number of moles at the high pressure condition is N high, we'll call it. So by the ideal gas law, N high is equal to P high times V divided by RT. The moles of oxygen is therefore the mole fraction times the number of moles. This is straightforward material balances. Okay, everything sounds not so bad so far, but here's where it gets a little bit trickier. During the vacuuming step, we're going to remove some of the moles, but the important thing to remember is that the mole fraction is going to remain constant. That's because we're not performing a separation process. We are simply removing some of the moles, and the moles that we remove have an equal chance to be oxygen or nitrogen. Well, not an equal chance, but the chance of the removal is proportional to the concentration. So if I start with 100 moles of air, for example, and all I do is vacuum out some of that air, whatever's left over inside is still going to be that same composition. The pressure at the end of the vacuum cycle we'll call P low. And just as N high was calculatable by the ideal gas law, N low is also the same thing, where I just replace P high by P low. Completely analogous logic. The moles of oxygen at this point is Y0 times NL. Now, in the second phase of the vacuum purge, we will relieve that with pure nitrogen. And this is going to change not only the number of moles in the vessel, but also the mole fraction, because now we're replacing it, we're diluting the oxygen, if you like. The mole fraction of oxygen is reduced, so we can calculate exactly how much. So the moles of oxygen is still the mole fraction times the number of low moles, but we've now added more moles. So this is just a new a way to update what the composition is. I'm taking the moles of oxygen and dividing it by the total moles. So we'll give it the subscript 1 because we've done one cycle at this point. And now what we do is we go through and we do the entire logic all over again. So after step 3 in this derivation, we cycle back up to step 1. We now know we're back at a high number of moles, and the moles of oxygen, instead of being Y0, is Y1 now. And you can see what's going to happen here is we're going to create a recursive formula So for example, Y2 is going to be equal to Y1 times N low over N high. But we already discovered that Y1 is equal to Y0 times NL over N high. So if we expand that out, what we find is that after J number of cycles, that Yj, the mole fraction of oxygen after however many cycles, is equal to the initial concentration of oxygen times the ratio of N low over N high to the J power. Let's talk about pressure purging next, and we'll talk about more holistically what this means or how we would solve problems with this. In the pressure purging scenario, it's the exact opposite logic, but again, very analogous. You add the inert first, and then you vent. So here we'll call N low atmospheric pressure because we're pressure purging it. So the higher pressure is going to be P high. Y0 is again the initial composition of oxygen. The first step is to add more inert to get to the high pressure. And here, when you do that again, you are diluting the composition of oxygen. So Y is going to change or be updated. So N high is equal to P high times V divided by RT, and the moles of oxygen stays constant in this step. I like to think about, again, do the moles of oxygen stay the same, or does the composition of oxygen stay the same for any given step? The new oxygen composition is then the same as it was. So we're updating. It's just the moles of oxygen divided by the total moles. And then you vent the pressure to return back to the original pressure. The moles goes back to NL while Y1 being constant. And the interesting thing that you find is that the equation looks exactly the same in both scenarios. So this was for my vacuum purge, and this was for my pressure purge. Note that it is the exact same. So although the final result is identical, you might think it doesn't make any difference to do a vacuum or a pressure purge, but actually that's not quite true because of the values of P high and P low. Remember, in vacuum purging, P high was 1 atmosphere, and in pressure purging, P low is 1 atmosphere. So practically, why would you want to do one versus the other? It's easier to pressurize a vessel than it is to pull a vacuum. If you've ever done a demonstration in chem lab, for example, where you pull a vacuum, you know it takes a while. And also notice that like you have a leaf blower, for example, and leaf vacuums do exist, but they're way less popular. If it were possible to have a pressure cleaner inside the house, you would do that instead of a vacuum cleaner, but that wouldn't necessarily solve the problem because you'd be blowing the dust all over your house. But the point is, again, it's always easier to blow and pressurize something than it is to suck something out or to pull a vacuum. Because of this thing about the P high and P low ratios, pressurizing usually requires more cycles since the high pressure is hazardous. All that means is that you can safely pull as high a vacuum as your pump will allow. On the other side, though, you can't arbitrarily just pressurize however high you want. Most vessels have a maximum allowable working pressure that you cannot exceed, or else you run the risk of compromising the integrity and having an explosion. The more cycles you use, the more expensive this is going to be because it's going to cost you more inert. So usually you can't get away with only 1 or 2 cycles with pressure purging. And I just mentioned the thing about structural integrity of the vessels. It really depends on what the vessel is and what it's designed to do. But be aware that not all vessels are the same. Some of them you can pressurize very well, but not vacuum. And then the vice versa is true too. Some vessels withstand vacuum well, but not pressurize easily.